Okay, I hope my screen is visible and I'm audible to you. Okay, so let's start today's session. So, welcome back to the 12th live session of Solar Energy Engineering and Technology. So, this is the last module that you have for this particular course. Um, okay, so what we'll do is I'll just quickly go through the uh, content within 30 or 35 minutes, and at last we'll solve some problem, mainly numerical problem. Okay, so in this particular module, the lectures are mainly focused on emerging solar energy technology, particularly your different type of solar cell, then your PV plus thermal technology, and then some solar field technology. Other than that, we also have your different application of the solar thermal in case of uh, your vapor absorption cycle and all that is discussed in the your next lecture, right? So okay, right. So I'll not go deep in the theory part. So basically this perovskite solar cell is a very new advanced technology in terms of solar PV, which has seen very recent development in terms of its higher efficiency as compared to way it was way back when it emerged in so 90s, and thereby leading to its lower cost only. So I think in current scenario, this this perovskite solar cell is a very hot topic for research, right? um, so this is nothing basically ABX3. So it's a sort of your organic inorganic metal halide. This is the chemical formula for it, general formula for it. And uh, it's basically used because it shows as advantages to our previous discussed solar cell type, is because it has strong absorption across visible region of solar cell, and weak excitation binding energy, a low charge recombination rate. So I'll not go much into detail. So you, but you should be aware about the theory part of this perovskite solar cell. What are its fabrication techniques? What are its advantages and disadvantages? What is the like just have to an idea about 23% this efficiency has also been seen recently in this perovskite solar cell. Okay. Now, so another one is this dye-sensitized solar cell. Um, Basically, it contains this particular four component. Semiconducting electrode is there. Then your dye synthesizer is there, where actually your light harvesting and electronic transition take place. Then you have your redox mediator and counter electrode. So the main advantage of this DSCC is your flexibility and lightweight, right? So it come into the thin film technology, your solar cell PV technology. Now, okay, quantum dot are basically nanoparticle sized semiconductor material. Where your whole electron motion is confined in 3D in a zero dimensional system, and uh, so whenever your light is enter through the transparent this electrode transparent electrode, then your into this quantum dot solar cell, your light absorbing layer of dot in order your electron hole pair is generated, and basically it's then separated to basically produce your electrical current. So that is whole idea about the quantum dot solar cell. Okay, so let's skip this part also. Okay, now this is PV plus your solar thermal thing. So what we are doing is, other than generating electricity by helping with the help of your PV cells, we are also utilizing the thermal energy. Okay, so we already know that this PV module will be at some temperature. So what we can do is we can utilize the this temperature of this PV cell to heat some another fluid, right? So it could be a water, it could be an air, and that combined system is known as PV thermal collector. Okay, so here different type of designs are there. So with we can see how by using this both PV thing and thermal thing in a combined setup, how the experimental electrical efficiency has like increased from 9.8% to 12.5%, or to some 27 to 87%. So we know that higher will be the PV cell temperature, more will be losses to the atmosphere, and lesser will be its electrical efficiency. So if its temperature is going to be lower, then your efficiency will increase. So that is whole idea about using this combined PV and thermal system in, and also you are getting some heated fluid that you can utilize for several applications, right? Okay, so if you want to calculate the different parameters of this PV plus thermal system, then we already know the electrical efficiency how to calculate. So it's basically your output over input, right? So your input is your incoming solar flux onto the solar PV into your area of the collector, and your output is your whatever power you are getting from particular module. Right. If you're talking about thermal efficiency, that's also we know how to calculate. The input power is this, and your output power is the basically how much temperature has been. We can calculate in terms of how much temperature has been increased for your particular fluid, which is with which your heat transfer is taking place. So your energy efficiency is now these two combined together. So since these two are acting simultaneously in series, that's why this plus signs come into picture, right? If it would have been in a parallel, then your multiplication should be there. So just trying to explain why this plus sign is there, by calculating for calculating this energy efficiency. If you want to calculate the exergy efficiency, then you know that it's exergy out upon exergy in, right? And your exergy out is your electrical plus your thermal thing. both are taking place simultaneously. So your electrical exergy, you already know how to calculate. It's basically your v into I, right? Your power, whatever you are going, and your thermal efficiency is given by this particular formula. Okay, so this is about this, how to calculate this output exergy, right? Input exergy, this particular formula is there, so I think you need to remember this both formula. Okay, both formula, this is easy one, you already know this two formula you need to remember to calculate this exergy efficiency, and numerical can be based on this particular formulas. Okay, for solar PV uh, and solar PV thermal combined system. Okay, now coming to solar fuel technology. So the concept of solar fuel technology is that you are storing basically or converting your solar thermal energy into some chemical bonds. So that is the concept behind the solar fuel technology, whatever you take. So let's skip this. Okay, so the most wide example, very new example and very hyped example is your water electrolysis, right? Using solar energy. So that is a very promising research interest uh, that produce green hydrogen. Okay, you might have heard many uh, policies coming about green hydrogen, right? So this is one of the very prominent way to produce green hydrogen. We are utilizing the solar energy, solar thermal energy, to basically do the water splitting. Okay, so here are some values given, whatever energy is required by gives free energy, like this much energy is required to particularly uh, basically do the water splitting to get your hydrogen. Okay, so this thing, your photo electrochemical water splitting is what I was talking about. The another thing is you can do it electrolysis of water by your electricity, that too can be generated from your PV module. Okay, so that could be also one of the alternative. Okay, as explained here, so from PV module you get your electricity, and this basically is particularly used to drive this electrolysis of water reaction. Okay, okay, we'll skip this theory part. You can. Okay, some of the other solar thermal application devices are this solar distillation. So what is this solar distillation? So we all are aware about the water crisis that we are having, the pollution um, leading to and also your excessive use of this groundwater that we have available, right? So that is leading to decrease in water level, groundwater level, underground water level, right? So okay, so solar desalination is one of the method. It's basically, if I just summarize it for you, then it's like similar to your water vapor cycle. So what happens is you have some saline water, or it can be a like your contaminated water. So with the help of solar radiation, we heat this water, the water evaporates, and then this is the glass surface we have. It gets condensed on this glass surface as it rises after heating, and then it trickle backs here, and then we basically collect this distilled water. So basically it could be a very useful application in a very remote area where we have water scarcity, and also we have not very fresh water source. This could be a very prime application of this solar thermal. Okay, so okay, so if you do the performance analysis of the solar distillation, what parameters you need to know is how much we are distilled water we are getting, maybe hourly basis or daily basis, by using this particular device, and what is the thermal efficiency. Those two are the important performance parameters. So um, basically numerical can be framed on this also. You need to remember how to calculate this for particular hour, say how much hourly distilled output in kg per meter square per hour. So it's um, you can, this formula you need to keep in mind. And efficiency, we already know how to calculate efficiency. So whatever energy is required to heat the water up till its your 100 degrees Celsius, and then whatever is the latent heat of your fusion, that will be your actual your basically output, right? Heat required, useful energy, right? And your input, you know already, whatever solar radiation is falling on your particular area of your your solar desalination setup. So these two formula you need to remember. Okay, so let's skip this theory part. Okay, this is box type solar cooker. So another application is solar cooker. You might have heard about it. Um, basically, the concept is similar to what we have seen. So we have this point. Okay, so we have this reflected mirror, and this is your glass cover, and this is your blackened surface. It is blackened aluminum tray, and here your pots are placed. So what happens is, as the solar rays fall onto this reflector mirror, it get reflected on to this basically your goes through this glass cover onto your pots, and some direct radiation are also following on this glass cover and then onto your pots that you have kept. So this is a very simple application. It's a non-pressure boiling type of cooking, where maximum temperature you can reach is approximately about 100 degrees Celsius, and the cooking time is basically preferred where your solar radiation intensity is high, that is in the afternoon, under clear sky condition. So this is one of the application of these solar thermal systems. And okay, so this is a example of community solar cooker. So if you have this several reflectors, and this is your cooking pot, so uh, uh, the capacity that it could be useful for, it could use basically the food could be prepared for 15,000 person per day if you are using certain number of reflector with certain area. And your 4,000 kg of steam per day at 180 degrees Celsius and 10 bar could be achieved by using this solar cooker. So you can understand that on a bigger picture, if you use this, it could be also one of the you can say sustainable ways of so there we might use it for preheating water that could be further used for cooking on a large scale in a community based system, right? Just to explain the application of this solar cooker. Okay, so okay, so if you do the thermal analysis, we know that for a few initial time there is a transient state, right? And after some time steady state, cause steady state is achieved. So, or a stagnation temperature is achieved of say 100 degrees Celsius. So if you do the energy balance and uh, th- uh, uh, so if you want to calculate how much time is required to achieve that particular temperature, you can use this formula, this derived formula. Okay, where the time constant used here is this T naught is can be calculated by this formula. This formula you have already seen again and again. We have done energy balance for several type of solar thermal application system. So this is a part where your input energy is there, your, and this is part where your loss is basically incorporated, right? And then we have also seen this collector efficiency factor again and again, right? So for solar cooker it's generally 0.85 it's taken. When we integrate both sides, and after this putting initial condition, boundary condition, we will get this formula. So this formula you need to remember. So let me point out what formulas are important. So this formula is important. How to calculate time constant, because this will be eventually used in this particular equation, right? And uh, this is basically reshuffled form of this formula. So these two formula you need to remember. Okay. Now this is the formula based on solar cook. Basically, this is the question based on solar cooker. So it has been asked to calculate the time taken for water at 45 degrees Celsius to boil in a solar cooker with the following specification. So average tau alpha value is given, your collector efficiency factor is given, your overall heat loss coefficient is given, your area of your basically cooker is given, right? Your MC heat and basically mass into a specific heat capacity of water is given. Okay, this product is given, your ambient temperature is given, your water inlet temperature is given, outlet, okay, because it is the temperature at which we want desired temperature, right? And your water TW boiling temperature is given, and your incoming flux is given. So basically on a solar cooker, okay, system, this 1000 watt per meter square is solar radiation falling, and we have been asked how much time it will take to heat the water at 45 degrees Celsius with this falling specification. So first we'll calculate the time constant, right? Which is your MC, your mass into specific heat capacity of water upon your collector efficiency factor into area into your overall heat loss coefficient. So, and then from here we can, after calculating that, we can put it in back into the equation. Okay, and we can calculate that this much time is actually required to heat the water uh, at 45 degrees Celsius in your solar cooker with the given specification and given irradiance condition. Okay, so just to show how this formula are utilized in actual scenario, we'll solve some numerical problem also. There I'll explain in, again this particular concept. Okay. Okay, this solar thermal energy could be also used for like desiccant cooling. So uh, basically the heat from this solar radiation, the heated fluid from this solar collector could be actually used to um, basically rid of the moisture content into particular sample. Okay, so that is concept behind this solar desiccant cooling. Okay, now this is aqua ammonia system. So uh, if I'll just explain whole system, uh, then if you okay, okay. So this aqua ammonia system is basically one of the refrigeration or your air space cooling methods. Okay, so we have our condenser, generator, evaporator, and absorber. This particular uh, uh, basically four component, major component is there. So if you want to have a cooled space here, so this is your desired cooling space that we want to cool. So what we do is the heat of this into okay, so just let me get a pointer. Right. So whatever heat is in this, if this space is want to we want it to cool this space, then whatever heat uh, uh, is in there in this space, that we need to first take off. So this heat is actually utilized to basically heat the this ammonia, aqua ammonia, this fluid system that is been flown in this basically um, what we can call. So this is evaporator section of this particular aqua ammonia system. Okay, so here evaporation take place of this refrigerant. So this aqua ammonia is used as refrigerant here. Okay, and then it's basically from here, from evaporator it goes to absorber, where this um, uh, basically your water to ammonia uh, ratio is maintained, and then it goes back to the condenser and then generator. So um, solar thermal energy is basically utilized for this generator system. Okay, to provide hot water to this generator system. So this I will explain in detail. We will solve one question and then we'll see how this actual system is being utilized by using this solar thermal energy. Okay. Okay, so there are a lot of theories that I'll just skip, and we'll so, go back to our questions. Okay. Okay, Mohat hazard, which factor affect the COP of aqua ammonia absorbing system? Okay, let me then switch back to another device, then I can explain you clearly. Okay, the question you have asked is, let me now go back to your question that you have asked. Which factor affect the COP of aqua ammonia absorbing system? Is there a concentration of water ammonia ratio? Okay, so this ammonia is actually your refrigerant and water is used as your absorbent. Okay, the first point is this. So we have this aqua ammonia system, right? So um, what happens is, okay, so let me use, okay, so just a minute. What's happening? So your COP of this aqua ammonia system actually depend on your whatever temperature is there of, if you see the formula, then it's basically, if you'll derive the this whole, you will do the second law analysis, and then if you'll derive the formula for COP, then it's basically depend on this temperature. Okay, so what I'll do, I'll just take one question on this aqua ammonia system, and we'll solve this question, and then I will clearly explain how this COP for this aqua ammonia system will be calculated. Okay, that I think that will be more, uh, then it will be more clear for you. Okay, so I have included one numerical on this particular aqua ammonia system also. So basically it depend on temperature of your generator and temperature of this condenser. I'll also show you how to solve, basically calculate this particular COP for this aqua ammonia system. Okay, so let me share it from another device where I can help you solve the, basically. First, we'll solve some theoretical problem. I've just included few, three, four theoretical problem, and then we can solve this numerical problem. Okay. Okay. So the first question is the theoretical question. Um, what are the fabrication techniques used for perovskite solar cell? Okay, I think you can mute yourself, Mohan. Any guess? So it's a very simple theoretical question. Uh, what are the fabrication technique for perovskite solar cell? Okay, let me give the answer. So, if you'll see the lecture, uh, then you know that all this method are method to fabricate this perovskite solar cell. You can do spin coating, or you can do spray coating, or you can do go for a vapor deposition method. So this all method are techniques, different techniques to fabricate your perovskite solar cell. Okay. Now the second question is sun tempering, shading, heat storage, natural cooling, natural lighting are important consideration for solar active, solar passive, architecture, or solar pond, or none of the above. Okay, let me give answer to this question. So, what is solar active and what is solar passive architecture? So, if you passive system means you are using the material, the design, the placement, or the structure to utilize the heat or light directly coming from the sun. But in active system, we use some devices. It could be electrical, okay, or it could be a thermal storage device also. Okay, so this basically active system utilizes these devices to convert the solar energy to more usable form. So it could be your hot for getting hot water, or it could be to get your electricity. So basically passive solar heating involves design structure, and active solar heating use collector and your storage devices or your heat pump to collect solar energy and then distribute it throughout your home or your building. So the sun tempering, shading, heat storage, natural cooling natural lighting are important consideration for solar passive architecture. So we are not using some mechanical aid, okay, into this particular system. So this is these all are important consideration or parameter for solar passive architecture. I think the difference between solar active and passive architecture is clear. Okay, now this is the next question. I'll read out the question first. So the overall solar to hydrogen conversion efficiency for a photo electrochemical water splitting having an operational current density of 9 milliampere per centimeter square and irradiance arriving at PEC devices 1000 watt per meter square is. So we have been asked about overall solar to hydrogen conversion efficiency for particular overall solar to hydrogen uh, basically conversion efficiency for your photoelectrical water splitting system. Okay, so I'll give some time to reflect on this question, and if possible try to solve this question, and then I'll explain uh, how to actually approach this question. Okay, Okay, let's see this question also. Any any luck finding how to approach this question? So this is your PV system, right? So here is where your water splitting take place. Okay, so it's a photo electrochemical water splitting. So this is this is your PV system on which your solar radiation of this 1000 watt per meter square. This is the standard uh, uh, test condition that we take at 1.5 air mass index, if you remember. So at this, the current density that has been generated is okay. So this current density generated from this photoelectrochemical system is given 9 milliampere per centimeter square, and your irradiance falling on this particular photoelectrochemical system is your 1000 watt per meter square. Now we know that uh, the required minimum potential for water splitting to take place is 1.223 electron volt is actually the minimum required potential for water splitting to take place. So if you want to calculate the thermal efficiency of this basically solar electrochemical system, then it will be your whatever current density that has been uh, produced by this particular system into your 1.23 electron volt, right? This is in right electron volt, and upon your whatever uh, power we are input. So the your input power is your 1000 watt per meter square. Okay, so if you put the values, then it will be your 9. It will be into 10 to power minus 3, so it will be ampere per centimeter square. Now for centimeter square, again we have to, so it will be basically 10 to power minus 4, right? And it is 1.23. Okay, and here your input power is your basically, if you write in term of irradiance, it will be your 1000, right, watt per meter square. If you want to calculate percentage, then multiply it by 100. So if we'll solve this, this will come to be 11.07%. Okay. Okay, so I hope this question is clear how to calculate this overall solar to hydrogen conversion system for a particular photoelectrochemical water splitting. So this is your input, right? Your solar irradiance coming on your this particular system, and your output is the generated electricity, right? So I think Alok, mic is on. Can you please mute yourself? Okay. Now, this is the next question. Calculate the time taken for 5 kg water at 30 degrees Celsius to boil in a solar cooker with the following specification. The average transmitted absorptive product is given, solar collector efficiency factor is given, overall heat loss coefficient is given, cooking area is given, specific heat of water is given, ambient temperature is given. Consider water boils at 100 degrees Celsius, we all know that, and the solar insolation available at the particular location is 950 watt per meter square. So we have been asked what is the time that will be uh, actually it will take to heat this amount of water at this particular given condition. Okay, so I'd like you to attempt this question, how to solve this question, and then uh, I will explain in detail how to basically solve this question. Okay, so Alok has raised his hand. Yes, Alok, you can unmute yourself and ask your doubt.
Yeah, madam, this is another question. Actually, I want to ask in PV module, we are using backseat.
Sorry, what?
Hello.
Yeah, yeah, you are audible in
In
PV module.
PV module, we are using. Yeah,
Yeah.
yeah, I am audible in PV module. We are using backseat. Actually, we are working as R&D.
Okay.
We are making PV backseat.
Okay.
So I want to know what is the actual structure and details like polymer base like EVA, PET, fluoropolymer is there. So can we take more discuss on these topics or we can
Okay, you want to discuss about your research that you are doing on PV backseat about the material that you are going to use,
yeah, yeah we
right?
yes and how the yes what is the testing condition of PV backseat in PV industries? Why this need for testing for this PV backseats? So I
Okay.
see the course I attend, complete courses I attend, but I no see this type of item details is there.
Right, right. So the content of this course was structured in a way that you have at the last of this particular course, you have the idea about what solar thermal, yeah, solar devices are generally there, and some important devices were discussed in detail. Basically, the thermodynamics, or you can heat transfer aspect, has been discussed in detail. So this particular thing is not in the
Yes, I
scope of
see.
this particular your subject, or you can say course. What you can do is you can mail me. You have my mail ID, right? You can mail me, particularly I will write my mail
Yeah,
ID, your particular query, and then we can discuss. What you can do is you can raise this question on Swayam portal also, but since this
okay.
question is out of the scope of this particular course, uh, I don't know, but you can actually mail me, then we can see what we can do for your particular research problem. Okay.
The, this is the same mail or
Okay, so I have
same mail or madam or you will give me another.
okay, okay. So I have include just written my mail ID in the chat box. You can mail me on that mail ID, and we can see what can be we can give our input for your
Okay,
particular
madam.
research
Okay.
query. Okay.
Oh, okay,
Okay.
madam.
Now I'll request you
Okay.
to just try to approach this question, and then we'll see how to solve this question in detail. Okay, let's see this question. So what are the values that is given in the question? So we are the system that we are dealing with is a solar cooker. Okay, so the average transmissivity absorptivity product is given, that is your zero point 0.8. Overall heat loss coefficient is given, which is 0.82. Okay, cooking area is given, which is 0.4 meter square. uh, okay, sorry, the overall heat loss coefficient is 6.65. It is in watt per meter square per degree Celsius. Your collector efficiency factor is given 0.82. Your specific heat of water that we already know, it is 4.18. It's in kilojoule per kg per degree Celsius. Ambient temperature is given 27 degrees Celsius, and the insolation is given 950 watt per meter square. Now we have been asked to calculate the time, right? So first we know the formula. First we need to calculate the time constant, right? So the time constant will be your mass of your water, that is your 5 kg. So mass of water is given 5 kg, and your temperature is also given 30 degrees Celsius, right? Now you know the mass of water, it's 5, right? And your specific heat capacity of water is 4.18, right? It's in kilojoule. Okay, so in joule it will be 10 to power 3. Now your f dash, your collector efficiency factor is 0.82. Okay, your area is given for cooking, it's zero point 0.4, and your overall heat loss coefficient uh, is 6.65. Okay, so when we'll solve this, it will be your value will be 9.582 into 10 to power 3. Okay, so it will be in second, right? So if we'll see it, it will be 9582 second. If we'll so this is your time constant. Now we know the time constant, we can calculate the actual time that will be required to basically heat this water. Okay, so we know the time constant, so let's put all the values. Okay, so this is the time required to heat 5 kg of water at 30 degrees Celsius to boil in a solar cooker. Okay, so uh, let's put the value. So it's 9582. This is the time constant into ln. Tau alpha is your zero point 0.8, right? Overall heat loss coefficient is 6.65. Then your temperature of water is your, and ambient is your 27, right? Divided by your 950 upon this will be zero point 0.8 minus 6.65 into uh, your initial water temperature is 30 degrees Celsius, right? And this is your ambient temperature, and this is your 950, right? So if we'll solve this, it will be uh, okay, this will be, if we'll solve this, it will be 0.289 divided by 0.779. So if we'll further solve it, it will be 9582 into your, this will come be point 99158. So 9501.36 second. So if we'll convert into minute, so we'll divide it by 60, then this your answer will be, so time will be 9501.36 divided by 60, so it will be some come near to be, I think it will be 158 minutes. Okay, so this is how you basically solve this type of question. uh, so I hope this question, this particular question on solar cooler is uh, clear to you. Okay, so basically we do the transient basically analysis, where we it might be given that given to find out how much time is required to heat this water, or uh, it could be other way around also. Maybe the time is given and then it could have asked how much temperature of water it has reached. Okay, so that could be also one possible frame for this particular question. I hope this question is clear. Any doubt in this question? Okay, let's move on to the next question. So this is a question on solar distillation unit. Okay, I'll read this question aloud, so it will be more clear to you while approaching this question. So for the solar distillation unit, the following data are available. The evaporative heat transfer coefficient from water surface to glass cover is given. Okay, heat transfer coefficient between water surface and glass cover is given. The temperature of inner glass is given. Water temperature is given. Saturation temperature of water, we know that. Latent heat of vaporization for water is given. Effective area of the solar still basin, that is also given in the question. Solar insolation is given, and we already know the specific heat of water. Now in the question it has been asked to calculate the what will be the hourly distillate yield in kilogram per hour. Okay, per square meter from this particular solar distillation unit. Okay, and then you can also further calculate what will be the thermal efficiency for the solar distillation unit. Okay, let's see this question. So we have a solar distillation unit. Okay, so this is your saline water, or maybe your contaminated water. And okay, so the heat transfer coefficient from water surface, these are glass cover. Okay, so what's given in the question is your heat transfer coefficient between this water surface and your glass cover. It's given 25 watt per meter square per degree Celsius. The temperature of inner glass is given 55 degrees Celsius, right? The temperature of water is given, so the water temperature is 60 degrees Celsius. What else is given? The saturation temperature of water, you know that, 100 degrees Celsius, right? Latent heat of vaporization, this value 22600 by 2260 is in kilojoule per kg. Okay. Effective area of solar still basin. So this effective area of the solar still basin is given 1 meter square, and solar insolation is given 950 watt per meter square. Okay, this value is given 950 watt per meter square, and specific heat of water we know that 4.18. This is in kilojoule per kg per degree Celsius, right? Now we have been asked what will be the hourly distillate yield. Okay, so we know that whatever heat is rate of heat is utilized to basically evaporate this water. Let's say it's QEW. Okay, this is actually a rate of water evaporation, the heat rate of heat transfer required to evaporate this water. Okay, okay, this can be written as mass of whatever water that we have got, distillate water, into your latent heat of fusion. Okay, this is actually, I hope you get this equation, how this equation uh, uh, is stated, right? So whatever distillate output we have calculated, the energy required to evaporate this water is given by this QEW. Okay, and this can in turn be calculated in terms of your specific your heat transfer coefficient from water surface to this glass into the difference in temperature of this your uh, water and your glass, right? Okay, so from here you can calculate this distillate yield. Okay, so it will be your, this is heat transfer coefficient into temperature of water minus temperature of glass upon your latent heat of fusion. If you want to calculate it for hour, then you will multiply it by 3600, right? So this is how this formula has been derived or comes into the picture. Okay, so we know the heat transfer coefficient, that will be your 25, right? You know the temperature of water, which is 60, temperature of glass is 55, upon latent heat of fusion is your this is 2260, right, into 3600. Okay, so this is in kilojoule, right? 2260 kilojoule, so let's write in joule. Okay, so if we solve this, then your value that will come, it will be mass of water will be it will come around 0.9199 kg per meter square per hour. Okay, so it will be equivalent to like 0.2 kg per meter or per meter square per hour. Okay. So the correct answer will be zero point 0.2. Now, if you want to calculate the thermal efficiency, so for thermal efficiency, the concept is clear, right? So for thermal efficiency, we know that it's output upon input, right? So your input is your incoming solar flux into your area of this particular solar still basin effective area, and your output is basically whatever heat, useful heat is there, right? So it will be whatever basically uh, so and so your this will be your sensible plus your latent heat. Okay, so it will be mcp into, so from 60 degrees Celsius, whatever heat is required to rise the temperature of this water from 60 degrees Celsius to its saturation temperature, and then at saturation temperature your phase change occur, right? So that will include your latent heat of fusion, right? So your mass of water into your latent heat of fusion for water. Okay, this is your actual useful heat that we get from this particular solar distillation unit upon your I into your A. Okay, so if you'll put all the value, you know the mass of water, you know the cp of water, you know the saturation temperature, and so let me, okay, so I don't have space, so let me write here. So it will be mass of water is your okay, so let me write it. So it will be 5.5, this value that we have calculated, right? So I don't have space. Okay, so basically you'll put all the values, and when you solve this, you know the I value, you know the A value, you know the saturation, you know the temperature of water that was at 60 degrees Celsius. So this will be 60, this will be 100, this will be 2260, right? And you can calculate the mass of water basically in kilojoule per second, right? That you will be required. So from here you can calculate in kilojoule per second, right? So mass of water will be your it will be your zero point 0.2, it's in 0.2 kg per meter square per hour, right? So if you'll divide by 3600, you can get it in, and for 1 meter square basin area, so we'll multiply it by area and divide it by your, so this hour can be written in 3600 second, right? 1 hour could be written as 3600 second. If you solve this, you can get your mass of water, which will come to be I think it will come 5.56 into 10 to power minus 5. This will be in kg per second. Okay, this is how you will calculate the mass of water in kg per second. This value will be actually used here. Okay, you know the cp of water, you know the t saturation, you know the, let me add one more slide and then I'll, it will be okay. So now let's clear solve this. So we know the mass of water, it will be that we have calculated zero point 0.2 kg per meter square per hour, that we have calculated in kg per second. It is 5.56 into 10 to power minus 5 kg per second. Now you know the efficiency formula. This is your sensible heating. Okay, from whatever temperature water is at to its saturation temperature into your plus your latent heat, right? Your input is your whatever flux is coming onto a particular area. So if you put all the values, it will be 5.56 into 10 to power minus 5. You can take m common. Okay, so it will be cp will be your 4.18, it's in kilojoule, so it will be in joule 10 to power 3, will multiply it by 10 to power 3. Saturation temperature of water is 100. The water in the basin was actually at 60 degrees Celsius. So this is basically to heat the water from 60 to 100 degrees Celsius, and then you have your phase change, for phase change, this latent heat of fusion. Okay, 2260, it's in kilojoule. Okay, so multiplied by 10 to the power 3 upon your incident flux was 950 and your area was 1 meter square. If you solve this, then your efficiency will be, so this value, if you solve this, it will be 5.56 into 10 to the power minus 5 into your 2427.2 upon 950. You are talking about percentage multiplied by 100, so efficiency will be 14.21%. Okay, so this will be your actual efficiency. Okay, right. So your correct answer is 14.12. Okay. So I hope this question is clear. Now we have this last question on your aqua ammonia absorption refrigeration system. I'll read this question. So in an aqua ammonia absorption refrigeration system, heat is supplied to a generator from an array of solar collector at 110 degrees Celsius. The temperature to be maintained in the refrigerator is minus 12 degrees Celsius and the ambient temperature is 25 degrees Celsius. Consider that the actual COP of this particular refrigeration system is 42% of the maximum COP. Okay, so there are two things that has been asked. What is the maximum COP of this particular absorption refrigeration system, and if the refrigeration load is 25 ton, what is the actual heat supplied by the solar collector? So these two are the basically parameter that you need to calculate. So I'll give you some time to reflect on this question and try to solve this question, then we'll see in detail how to actually approach this question. Okay. Okay, let's see this question. So first, let's understand what actual aqua ammonia absorption refrigeration system is. So it's a type of vapor absorption refrigeration system that uses ammonia as a refrigerant and water as an absorbent. Okay. So if you see how this work is, uh, this is your evaporator. Okay. So this is your cooling space. Okay, whatever cooling space is there, that need to be cooled. So the heat from this cooling space is used to evaporate the ammonia. Okay, liquid ammonia. So here it has liquid ammonia that will get basically the you can get the basically vapor ammonia by using the heat from this particular space that need to be cooled. So after giving heat, this obviously this space will be cooled. So from here we get your vapor ammonia. Okay, so here we have low pressure ammonia vapor. Okay, this goes into your absorber unit. Okay, in absorber unit what we have this your ammonia plus water. Okay, so we have this lean aqueous solution of ammonia in our absorber, and as this low pressure ammonia goes into this absorber unit, this turns this lean mixture into your rich solution with ammonia, right? And uh, we know that the solubility of ammonia is inversely proportional to temperature. So the more absorption will be there at lower temperature. For that we use this cooling. Okay, to keep this absorber unit at lower temperature, so more absorption of ammonia into water will take place. Okay, now um, from this rich solution, the next step is your desorption that occurs in this generator. Okay, so here we get our basically strong ammonia water solution. So at this point, after getting our rich mixture, we have here your strong ammonia your water basically solution, right? This is the pressure valve, reducing walls to basically. So what happens is this strong ammonia now strong ammonia water aqueous system is now goes to generator, where heat is utilized basically to desorb ammonia from this rich solution. Okay, so here is where your solar energy comes into the picture. Okay, so this gaseous ammonia is dissolved from the solution at high pressure to generate again this lean solution that can be sent back to this absorber. Now at this point we have this dissolved, like your gaseous ammonia at high pressure, right? Now we have high pressure ammonia vapor here. Now the next step is the condensation. So in condenser what we do is we basically cool this high pressure ammonia to basically what the aim is of using condenser is that at this point the ammonia vapor temperature is very high, right? So we cannot feed a very high temperature ammonia into the cooling space, because in that case basically your evaporation will not take as effectively as we if we feed low temperature ammonia, right? So all role is of the temperature of this particular space that we have, and the temperature of the ammonia that we are feeding into your this system. So greater will be the temperature difference, more will be the heat that can be taken from this particular space. So that is the concept. So that's why you are using condenser basically to reduce the temperature, right? So we have your low temperature high pressure ammonia here. Okay, so now we have liquid ammonia, right, after condensation. Now expansion valve is used to basically lower the pressure. So we have low pressure, low temperature. Okay, liquid ammonia here. Now this liquid ammonia is finally fed to your evaporator, and this cycle goes on. So this is your whole uh, aqua ammonia absorption refrigeration system. So if you see, okay, let me explain in detail. So if you see, this is your source. Your ammonia aqua ammonia refrigeration system has four important units. One is generator, another is condenser, uh, then we have your absorber, right, and we have your evaporator, right. And this evaporator is actually taking heat from your cooling space. The space need to be cooled, whatever reason it may be, right, say at temperature tr. Okay, now this is your basically absorption unit, your ammonia, your refrigeration unit. This is the four main component, right. Now we'll see how heat transfer is taking place in which region. So from your region that need to be cooled, heat is taken from the system, right, out of the system. Say that heat be represented by QE. Okay, now another heat transfer is taking place between your generators. So some heat is required for deabsorption that we get from that we can get from any source. Say it might be the solar in this particular question. So we are taking some heat into the system from this particular source. So say this heat is represented by Qg, and your source is at temperature T1. Okay, now there is some heat transfer between ambient also and your system also. So where that heat transfer is taking place, so first one is in the condenser, right. So in your condenser your heat exchange is taking place, and it is being transferred to the atmosphere, right. So say sink or atmosphere which is at temperature 32. Okay, uh, again, in absorber also your absorbers are cooled to increase the absorption of ammonia into the water, right. So here also, so let's say it's QC for condenser, heat taken from the condenser, and your QA for absorber. Okay, so this is all the heat transfer that is taking place between source, your particular region that need to be cooled, your aqua ammonia refrigeration unit, and your atmosphere. I hope this particular uh, uh, whatever I have explained, it's clear how heat transfer is taking place between different component of this particular aqua ammonia absorption system, right. Now if you, by the first law of thermodynamics, if we write the heat balance, then heat in will be equal to heat out, right. So it will be Qg plus QE is the actual. So this is the system that we are talking about. Okay, this is the system that we are talking about. This is the aqua ammonia refrigeration unit. In this unit the incoming heat is from this particular region that need to be cooled and your source, right. So it's Qg plus QE, and the heat going out from the system is basically from the condenser and absorber, right. Now if you write the second law from second law of thermodynamics, so change in entropy of your source plus your sink and plus your this particular region, this should be greater than equal to 0. So these are the two equation So if we write this second law in terms of heat transfer, so it will be your source is this, right? So entropy change of the source will be, so basically heat is going from this source, so it will be minus qg upon the temperature of this source, right? For sink, heat is coming into the system, so it will be positive, right? So qc plus qa upon the temperature of this sink is T2, and plus your for region heat is going from the system, so it will be negative, right? So it will be qe upon temperature of the particular region, right? It should be greater than equal to 0. So these are the two equations from which your COP will be calculated. So basically COP equation could be derived. So if we'll just I'll just solve it quickly. So it will be minus qg upon t1, and this qc plus qa can be written as qg plus qe, right? So it will be qg plus qe upon t2 minus qe by tr should be greater than equal to 0. So if we'll now see that the all the term is in the form of qg and qe, and what will be qe by qg? If we let me rearrange it quickly, solve this. So it will be uh, basically qg 1 by t2 minus 1 by t1, and it will be qe 1 by t2 minus 1 by tr greater than equal to 0, right? Now if we'll solve it further, then so qg could be written as 1 by t2 minus 1 by t1. So it could be written as t1 minus t2 upon t1 t2 uh, plus qe. It was 1 by t2 minus 1 by tr. So it will be tr minus t2 upon, this will be tr into t2 greater than equal to 0. So qe by qg, this is the point of interest here. So qe by qg will be, if we'll solve this, it will be basically t1 minus t2 upon t2 minus tr into tr upon t1. Okay, so what this qe by qe represent? QE is your basically your desired output, that was to uh, cool the particular region, right? And your qg is basically your input to the system given, right? So that was from the source, right? In the generator, right? So this is your input energy, right? So this is actually your COP, coefficient of performance. And if you want to talk about what will be the maximum COP, that could be, so this COP will be always less than equal to this value. If we talk about the maximum COP, it will be equal to this particular value, right? T1 minus T2 upon T2 minus TR. Okay, so this will be, if you note this particular formula that we have derived, you'll note that this is basically ideal COP of refrigeration cycle between your T2, your sink, and your cooling space. And this T2 by TR is actually ideal your thermal efficiency of heat engine, right? That is working between temperature T1 and R1, T1 and TR, which is basically, I'll show you. So there is two thing going on simultaneously. This whole system could be understand in term of two component. One is the heat engine and one is the refrigeration unit. So the heat engine is working between this source and your sink, right? And refrigeration unit is working between this particular cooling space and your sink. Okay, just to understand how this formula could be understood, right? So we got the COP max formula, right? Now we'll see what is given in the question. So okay, in question Okay, so what was given in the question is the heat is supplied to the generator from array of solar collector at 1 at 10 degrees Celsius. So this is actually uh, basically T1 temperature, right? This is your source temperature, right? The temperature to be maintained in the refrigeration is minus 12 degrees Celsius. So this is your basically TR temperature, right? For the region. And the ambient temperature is your 25 degrees Celsius. So this is your TA temperature, ambient, or you can, in this case that I have explained the notation, this is T2 temperature. Now the COP actual is told to be 42% of COP max. We already know the formula for COP max. Let's write this formula. So first, write the temperature. T1 was 110 degrees Celsius. Note that in this formula, all the temperature must be put in Kelvin. Okay, so it will be 110 plus 273, which will be equal to 383 Kelvin. T2 was I think ambient temperature was 25 degrees Celsius, which will be 25 plus 273. It will be 298 Kelvin, right? And T3 temperature or TR temperature was minus 12 degrees Celsius, right? So it will be minus 12 plus 273, right? So it will be 1, this will be 6, and this will be 261 Kelvin. Now, COP maximum will be your T1 minus T2 upon T2. This is for refrigeration cycle and this is for heat engine. So TR upon this was your T2 minus TR, right? So it will be T1, we know it is 383 minus 298 upon 383, right? And TR is your 261 upon 298 minus 261. So if we solve this, it will be 1.566. This is your COP maximum. Okay, so this is the correct answer. So 1.5. This is your correct answer. 6 is. And the next is refrigeration load is given 25 ton. What is the heat supplied by the solar collector? So what is the given is refrigeration load is given. This QE is given, right? Refrigeration load means what is the basically load required to heat the particular region. So this QE value is given. We have been asked about what is QG value, right? The heat supplied by the solar collector. That has been asked. So let me add one more slide. Okay. Now we have calculated the maximum COP, that was 1.566. The actual COP is already mentioned in the question that it is 42%. Okay, 42% of COP max, right? So we can calculate the actual COP. It will be 42 upon 100 into 1.566. This will come to be 0.676575. Okay, this is your actual COP. Okay, now the actual your QE was given in your 25 ton. It was given. So note that pay attention to the unit also. So to 1 ton is equal to 14,000 kilojoule per hour. So it will be 14,000. This will be kilojoule per hour, and per hour could be, the hour could be written in second. So it will be second, right? Kilojoule per second. So if we'll solve this, we will get 97.22. It is kilojoule per second, or you can write it as kilowatt. Okay, so now you know the value of q, you know the COP actual. So what is the COP actual is actually coefficient of performance is basically your basically what is the desired thing that you want from the whole system, that is for the cooling the space. For that you know the value of QE, and the input energy for that particular unit is your coming from solar, right? So that you need to calculate, that is represented by qg, right? So we can put the value. So uh, 0.6575 is actually equal to your QE is basically 97.22, and QG is your that you need to calculate. So if we'll put solve this, then your QG will be basically uh, 147.86, or we can say 148 kilowatt. Okay, so this is your answer. Let's see. So okay, 148 kilowatt is the answer, right? So I hope this aqua ammonia absorption refrigeration system is clear. Um, uh, um, so uh, Mohan has asked the question. So I hope this whole aqua ammonia absorption system, how to solve this, how to calculate this COP, maximum actual COP, how to calculate what is the actual heat required from the solar collector. All this is clear. Any doubt in this question? Okay. If there is no doubt, uh, okay. I will end this session. We are way beyond our time limit, but actually needed to explain this question because it was your particular doubt. So I hope this session was useful to you. Um, and This is the last official live session for this particular course. I will take one more doubt clearing session. I think it's probably scheduled tomorrow. You will get the notification. That session I will mainly try to cover the numerical problem. So I hope this session was useful to you, and we'll meet in the next probably session. That will be our last session. If so, thank you all for listening.